Okay. So just a few things before we go ahead and get started. A few housekeeping items. I'm going to go ahead and give you your next homework assignment today because we should be able to wrap up this lesson pretty quick. We're going to have it due tomorrow, so you should have time in class to go ahead and work on it. Thursday, we're going to have a quiz over this material. Now, we did start by talking about relations and functions just very briefly. That's the next lesson. The quiz is just going to be over this type of material right here. I might go ahead and give you just a couple of sets and say, okay, what's the intersection? What's the union? What's the complement? So basically, it's going to be very straightforward. That's on Thursday. And then the big one's coming up next week on Thursday the 30th. That's your what? That's your test. Okay. So we're going to see how far we can get. We do have another lesson. We'll start tomorrow where we focus a little more on functions and relations. Then we're going to move into piecewise functions, and we'll go ahead and start talking about rational functions. So we'll see really how far we can get by the time next Thursday rolls around. But any questions? Okay. Did everybody get the text I sent yesterday? The practice one? Okay, so if you've been gone or if you hadn't copied it down, right there in the middle on the backboard, Pre-Cal Academic, if you wanted to go ahead and sign up for Remind 101, just for some extra reminders, quizzes, tests, things like that. So I'll probably be sending another one tomorrow evening. Hey, don't forget about the quiz. You know, if you need tutorials, I'm here in the morning. So it is at G7G Cha. All right. Well, let's go ahead and get to it. How far did we get? I don't remember. Did we at least get to this part? What's that, Brandon? Okay, so we were on the other side? On the other side. Well, no, 3B. You said 1B, I'm sorry. Okay, so that's as far as we got. Okay, so I think we were just listing the sets and telling whether they're true or false. I think everybody was having an all right time with those, unless I'm mistaken. Do I need to make up another one, or are we good? What do you guys think? Let's make up another one. Okay. Let's say, set B is all values. So let's say all X. What was that colon again? Such that. And then we have our restrictions. So let's say X is a positive integer, and we'll say less than 10. Okay. And there we go. So that's one of the things we're going to go ahead and talk about today. Z is the letter that represents what we call the group of integers. Okay. And since I put a little plus there where a power would be, that tells me I'm only looking at the positive integers. Okay, because the integers can also contain their opposites, the idea of subtraction. So what is set B exactly? Like, what's the first element? It's strictly positive, so we can't include what? 0. 0 is neither positive nor negative. Okay, so 1, and we go through what? Would it include 10? No, because we're less than. Now, if I had equality, then we'd include that. So B is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I'll just give you a couple of statements here. Let's say 0 belongs to B, and let's say 6 belongs to set B. Okay. So based on this set, is it a true statement to say that 0 belongs to it? No. 0 we just said is neither positive nor negative, so that would be false. And what about 6 belonging to B? That's a true. Yeah, we can absolutely see 6 right there. It's a positive integer less than 10. There we go. And that's what we left off with yesterday. Okay, I want to kind of continue the idea intersection and union. So let's do a quick review and to kind of help out the folks who weren't here. We have union. We have intersection. So union, intersection. If I could spell, that'd be great. So what were the two symbols we used for union? A U and a V. Okay, so both capital letters. So U and a V. What was the key word there? Okay. Or. There we go. That's what I'm fishing for. So or. What were the symbols when it came to intersection? Okay, the same capital letters but upside down. So we have basically an arch, as some people are describing it. And then we have the upside down V. And what's intersections word? And. Okay, now what's the difference? What do I mean when I say union, for example? It's with it. Everything together. Good. The way I described it yesterday was a marriage. We're going to take every element in one set, every element in another, and we're just going to combine them into one bigger set. Okay, so how does that differ from an intersection? Only the parts that are the same. That's exactly right. Only the elements that they have in common. If you were to look at it visually, like with a Venn diagram, you'd see they overlap. Okay, good. Very good. And then we also talked about one other word, or I don't believe we got to it. No, we didn't get to it yet. Okay. So let's do this. Those other classes got a little further than we did, and that's okay. All right. So we were talking about the idea yesterday of a group within a group. What do we call that? That's a subset. Very good. And we talked about our class being a subset of Lubbock High. So now let's talk about the universal set. It's the set of all possible elements for a situation. Of course, there's a typo there, so period, capital. All other sets in the situation are subsets of the universal set. In a Venn diagram, sets are represented by shapes, usually circles or ovals. The elements of a set are labeled within the circle. Okay, so you'll notice here, we're given sets A and B. And because B is made up of 1, 2, 3, you see 1 belongs to set A, 2 belongs to A, 3 belongs to A, well, we can say B is a subset of A. So visually, we can see that group B is completely contained within group A, but it's all still within the universe. Now, the universe can have an infinite number of items, but for our purposes, we'll most likely be dealing with finite. There'll be some kind of survey or something taken. So if there was, say, an intersection, but B wasn't a subset, you might have something like this. Okay. There's only the one region where they overlap, the one intersection. Okay. You still have elements in each that don't belong to the other. Does anybody remember what we called it if they don't intersect? Started with an E or an N. Or we could use this symbol. Okay, the no solution. If they don't intersect, we can say that they have the empty set. It's the null set. Okay. In fact, you'd probably have a Venn diagram that looks like this. Those two circles are in your universe, but they don't interact in any way. They're just right next to each other. Okay, good. But what I want to go ahead and talk about on this page is what we call the complement. Okay, it says the set of elements in U that are not elements of set B is called the complement of B and is written B with a little tick mark. So you might remember that from geometry when you were doing, say, transformations. You might have called that the image or even said prime, which is perfectly fine. But when we're talking about sets, this is how we go ahead and describe the complement. So that means we're talking about all the elements that are in the universe, okay, but not in that particular set. Okay, so it might be a little confusing, and that's okay. Let's take a look at some examples. All right. So let's say the universe, okay, if we were to go ahead and diagram this as a Venn diagram, only contains these 10 elements, 0 all the way through 9. Those are all the numbers we're going to work with. And then you have sets A, which is 1, 4, 5, 7, 8, 9, B, 5, 7, C has 4 elements, D has 2, and E has 2 as well, right? Okay. So let's go ahead and start working some of these. First off, state whether B is a, what does that mean? That was the symbol we used for subset, the group within a group. So let's look at the elements of B. Okay. B has 5 and 7. So could I say that 5 belongs to set A? That's a true statement. Okay. This is just like we were doing a second ago. All right. The other element is 7. Could I go ahead and say that 7 belongs to A? Yeah. So with both of those being true, can I say that B is a subset of A? Yeah. Yes. So that's a true statement. Okay. That's all there is to it. Right, Nathaniel? Right, Nathaniel? Right, Nathaniel? Right. Okay. Let's try 2B, or not 2B, maybe. It's a little joke there. Okay. State whether E is a subset of D. Okay. So, Kanal, you're saying what? You're already saying false. Why? What's up? There you go. Now, see, 3 does belong to set D, right? But does 6? 6 does not. So if all the elements of one set don't belong to another, you can't say it's a subset. Yeah, so that's false. Okay. Did anybody want me to go ahead and write it out like I did the previous one with the belonging to symbol? You do? Okay. So we can go ahead and say that 3 does belong to D. That's a true statement. But 6 does not belong to D. So because we have one element of E that doesn't belong to D, I can't say it's a subset. We don't have that group within a group. Okay. Now here's that last vocabulary word we just brought up. What does that little tick mark mean? This means the complement. Okay, so we're looking for every element contained in the universe, but that is not, in this case, set A. All right, so let me go ahead and give myself a little bit of room here. So I only want to focus on these two guys right here, the universe and A. So I want everything in the universe not containing A. So an easy way to do it, all the elements of A that you find in the universe, mark them out. So see, A has 1, so I'm going to mark him out. And he also has what? 4, 5, 7, 8, 9. So 4, 5, 7, 8, 9. The complement is everything that's left in the universe outside of that set. Okay, so it's only 4 elements. What would it be? 0, 2, 3, and 6. That's it. Okay. That's what the complement means. All the elements that are not in that set, but still in the universe. Is everybody okay with that? Does anybody have any questions? Okay. Well, let's try the same thing for D. Okay, so I'm going to go ahead and erase these right here. All right, so I want to look at the universe and set D, which has elements 2 and 3. So I'm looking for all the elements that are in the universe, but not found in D. That's the complement. So is there going to be more elements than the previous one? Yeah, what's the only ones we have to throw out? 2 and 3, because they're in D itself. So I want 0, 1, and then I want 4 through 9. 4, 5, 6, 7, 8, 9. Is this making sense? Okay. Do we want to do another one, or you feel confident? Okay. Does anybody want to do another one? All right. Then let's see what else we got. Okay. If two sets have no elements in common, their intersection is the empty set. Or we can also call that what? Starts with an N. We could say no solution. You're absolutely right. Or the null set. Okay, so any of those can be used interchangeably. Any of those could be your answer. All right, so let's say we have another one of these. So the universe only has elements 1 to 8, so that's all we're dealing with. Then it says R has 3 elements, 2, 4, 6. S has 4, the 4, 5, 6, 7. And T only has 1 element, just the one itself. Okay. So what is 3A asking me to find? The union. Okay, so we need to know those symbols. Does that mean I just want to combine those two sets, or I'm just looking for what they share? I want to combine them. So I'm going to take everything I see in R, everything I see in S, and I'm just going to write it as one big group. But what if they have elements that repeat? Do I write them twice? No, I don't have to. Okay, so I'm going to start with 2, and then what? 4, 5, 6, 7. I took all of these 3 and those 4, and I just combined them. If they repeat, I don't have to write them again. The union is simply to bring them together. Okay. Let's take a look with the next one. So if 3A wants the union, what's B? It wants the intersection. So what does that mean again? I keep forgetting. What they have that's in common. Okay, so what does set R have that set S also has? 4 and 6. Okay. There we go. That's the difference between the union and the intersection. The union is what they share. The union is everything, the combination. The intersection is what they share. Excuse me. Okay.
Would you want us to write R union S and S equals 2, 4, 5, 6, 7, or do you want us just do brackets?
Oh, since we're talking about sets, let's use those squiggly brackets. That's a good question. Yeah, so it's just the notation we use to say that they do belong to one group, one set. Okay. All right, let's try C. So what do I want to do with T and S? What they have in common. I want the intersection. So what's in S that's also in T? Nothing. So what would that be? No solution. Okay, we could say it's the empty set. We could say it's the null set. Okay. I'm going to go ahead and give you another one of these. Okay. Let's try, oh, okay. All right, now specifically, what am I asking you for here? The intersection. Okay, the complement's part of it, so I want S's complement intersecting with R. Okay, so it might help to go ahead and write these down. Now, R, we want set R itself. We don't want its complement, right? So I'm going to go ahead and write R right here. And if you're able to do this visually, fantastic. You know, if it helps you to write it out, you know, go ahead and do so. So R is 2, 4, 6, right? Okay. Now I want to intersect that with the complement. What was the complement again? I keep forgetting. Okay, so everything that's still in the universe, but what? But not part of the set, in this case, S. So these elements, 4, 5, 6, 7, that belong to S, the complement won't have those. So 4, 5, 6, 7, they're gone. So what's S's complement? 1, 2, 3, 8. So 1, 2, 3, 8. So do we have an intersection between R and S's complement? Yes, what is it? It's 2. There you go. Okay. And these type of problems right here, this is what you can expect your quiz to be. Okay. It's going to be very, very similar. I'll give you some sets, and then you'll just go ahead and tell me what the unions and the intersections and the complements are. Okay. Any questions on that? Okay. Now, why don't we go ahead and do this? It doesn't say to, but let's go ahead and draw a Venn diagram to kind of help us out. All right. Now, typically, I'm not going to be that big of a stickler on this. Typically, though, like in statistics or certain classes, your teachers are going to have you put a U here, and they may go ahead and have you put the number of elements that you have in the universe. I'm not going to really be looking for that. I'm going to be looking more for the Venn diagram itself. Okay, so I want to draw a Venn diagram. This is the universe that has 1 through 8. It has sets R, S, and T, right? Okay, so let's think about this. What's the relationship between R, S, and T? Do they all intersect? Do none of them intersect? Do only 2? Only 2 of them, and actually we found that with 3B, right? We know R intersects S. So how am I going to draw that? Yeah, okay. And then like you said, the one off to the side. So we're going to have 2 circles that are going to slightly overlap, and then you said one off to the side. Yeah, what's that one going to be? That's T, because T is still part of this universe, right? But he doesn't have any relationship with R and S. He just has the one element. Okay, so let's say that this one on the left represents R, this is S. And really it doesn't matter as long as you label them. Okay, so we already figured this out. What do R and S share? 4 and 6. So I'm going to put 4 and 6 right here in the overlap. Okay, that's the visual representation of the intersection. So does anything else belong to R besides 4 and 6? 2. So I'm going to put 2 right here. Okay, because while 2 is a member of R, he's not part of the intersection. He also does not belong to S. So what should go over here that just belongs to S?
5 and 7.
Hey, 5 and 7. Is everybody seeing how I'm constructing this? Does anybody have any questions, problems? Now, are we done? There's something we're forgetting. Well, no, we got the T. So, Brandon, you said what's in the universe? So, okay, well, let me ask the question this way. Are there any numbers that don't belong to these sets that we haven't written yet? 3 and 8. 3 and 8, they're part of the universe, but they don't belong to any of those sets. So somewhere in the rectangle, I just have to go ahead and put 3 and 8. Because they're still part of this, they just don't belong to those sets. Okay, how we doing? questions? Okay. All right. Well, the only other thing I have right here is that if you were to have a Venn diagram with two sets that don't intersect, okay, we can call those disjoint. Okay. So sets, we can also say they are disjoint if there's no intersection. And then just a little bit more vocabulary word. What's this symbol right here? The upside down V? That's the intersection, right? Okay. So the intersection, we're describing that also as a conjunction. So this is just another vocabulary word. Okay. So instead of intersection, we can say conjunction. So what do you think disjunction is? That's a union. So this is a union. Conjunction is a intersection. Perfect. Okay. All right. How we doing? All right. I'm thinking probably 5 minutes, maybe not even that. Unless anybody has any questions, we're going to be done. And then I'll go ahead and give you your assignment. We'll go from there. The only other thing I want to talk about is how to classify numerical values. Okay. So up to now, okay, this is probably the one you've been working with. Some of you may have gone a little further and expanded it. But up till now, you've said everything is real, correct? Well, what two groups make up the reals? The rationals and the irrationals. Okay, so if a number is irrational, it has no subgroups, no subsets. So we stop there. If it's rational, then it could be an integer, whole number, or a natural number. So why don't we go ahead and start by just defining those. And you'll notice down at the bottom, you do have the mathematical notation definitions for those. So can anybody tell me, what are the natural numbers? Yeah, they were the first counting numbers that you ever learned. Okay, so the natural, which we call n, is just 1, 2, 3, ... Okay. Now, the whole numbers and the natural numbers are virtually identical. The whole numbers have just one extra value, 0. That's the only difference. So the whole numbers start with 0 and then 1, 2, 3, ... Okay. So the groups expand as you get older because you started getting taught more ideas, more different concepts. So what separates the integers, the z? Brandon? Negatives. So it contains 0, your positive counting numbers, and their opposites. So this one, ... let's say -2, -1, 0, 1, 2, ... Okay. But the one thing you're going to notice about integers, whole numbers, and natural numbers, we don't see any what? No decimals, no fractions. Okay. If it's a decimal or a fraction, the furthest you can go is rational. And that is the actual definition. If you look at this guy right here, okay, it says Q, which is your rationals, all the values that can be written in a fraction A over B, such that A what? What does that curvy E mean? Belongs to, is a member of. Z, the integers. Is that and or? And, okay, B belongs to the integers, and B can't be 0. Yeah, that makes sense, because what's the one thing you can never divide by? 0. It's undefined, so we have to have that restriction. Okay. Now, let's talk about the irrationals. What's probably the most famous irrational number we have? Oh, the 1/2 isn't irrational, it's rational. Okay. You use this a lot in dealing with circles? Pi, okay. Pi. There we go. 3.141592653589793. Yeah, it keeps going, right? But there's two conditions that'll classify a number as irrational. So think about pi. What do you think is going to make him irrational? Christian, say it louder. It goes forever. It has a non-terminating decimal. Okay, it never stops. Okay, so that's one. One other condition. 3.33? Oh, I think you're close. You have to look for something. If you see a what? There we go. Okay, if there's any pattern to the numbers, if it's the same number repeating or same group of numbers repeating, if there's a definite pattern and it goes forever, that's rational. If it goes on forever, but it's just a bunch of random digits, that's irrational. Okay, good. And then everything, of course, is real. So now at this point, we're going to expand it one more time. We're going to introduce you to the idea that the reals are now a subgroup or a subset of what we call complex. Okay, and you might remember this from Algebra 2 when you dealt with imaginary numbers. Complex numbers are going to be in that form. Okay. I got a text. Okay. So A is your real portion. BI is the imaginary unit. Okay. Now, we're going to go ahead and change this. Normally, irrationals we would go ahead and call the capital I. But now that we have imaginary included in this, we're going to say I represents the imaginary, so you have one of two choices for irrational. Okay, I prefer the first one, the R minus Q, because think about it. If you have the entire group of reals and you subtract off the rationals, what are you left with? The irrationals. Okay, or you could also put R slash Q, but that's probably the thing that people are forgetting most often, because they're so accustomed to saying I for irrational, and it's really easy to do. But we're going to say I is imaginary now. Okay, so let's practice doing this. Give me a number. That's all right. So what value would you like B to represent? 7. Let's say 7. Okay. Now, some people like to start at the bottom and work their way up. I like to start at the top and work their way down. What do you think, Nathaniel? What do you like to do? You like to start at the top? That's my man. Okay, so we're going to start at the top. Can 7 be called complex? Yes. And think about this. Is 7 real? And the reals belong to what group? Complex. So it's going to look a little strange, but I can write 7 in that form just by saying 0i. Okay, that is still legitimate. Okay, because I can do that, I can still call it a complex number. Now, if it doesn't have the imaginary unit, I can't call it imaginary. So I'm going to start off by saying it's complex. So everything we're going to deal with is always going to be complex, because complex is the biggest group. Now, what are you going to say? Real or imaginary? It's definitely real, so it's not imaginary. And now we have one more choice. Now that I've chosen real, is 7 rational or irrational?
Rational.
It's definitely rational. Remember, the definition of rational was that it could be written as a what? As a fraction. How could I write 7 as a fraction? Yeah, just put 7 over 1. It's the same value, right? So it is a rational number. And now we just work our way down. Is it an integer? Yes. Is it a whole number? Yes. Is it a natural number? Yes. So 7 belongs to a lot of groups. Okay. That's the last part of your assignment. You're just going to be telling me what groups they belong to. Okay, let's try another one. What about negative 2/3? We'll just start at the top. Is it complex? Absolutely. Everything can be labeled complex. Is it real or imaginary? Real. Okay, we know it's not imaginary because there's no I. Okay, even if I put plus 0i, it would have to have something besides the 0 in front. Okay, so this is real. Now, rational or irrational? This is, was it? Rational. Remember, because by definition, rational means it can be written as a fraction, and negative 2/3 is a fraction. And now we just keep going. Is it an integer? Oh, Canal says no. Why? There you go. That's as far as I can go. Remember, integers, whole numbers, natural numbers, no fractions, no decimals. Okay, so that's as far as, so he only belongs to 3 groups. Okay. Is everybody starting to get the idea? Easy? Now let me go ahead and give you one more. Now sometimes I might get a little tricky and ask you to go ahead and simplify before you tell me what groups they belong to. What if I gave you the square root of negative 36? Oh, it's not negative 6. It is 6i. There we go. This one's definitely imaginary. Do we want to go through that? Do you guys remember that from Algebra 2? Does anybody want me to kind of elaborate why? Yes, okay. Well, here's the thing. If you're taking the square root of a number, like square root of 36, we know that's what? We know it's 6, but why? Because 6 times 6. You're looking for the factor you multiply against itself, right? It has to be the same number. Well, if we have a negative number, we still have 6, but one would have to be positive, one would have to be negative. And the fact that one's positive, one's negative, those are not the same number. And that's the problem we run into. So what we do is we go ahead and break the negative away from it. It's kind of like we quarantine it. We don't want to deal with the negative. We still want to simplify the radical. So the square root of 36 times negative 1. So I can write that as the square root of 36 times the square root of negative 1. It's kind of like we're pushing him to the side so I can still simplify the problem. What's the square root of 36? 6, and this is what we call that variable I. Okay, we've just labeled it as such. That's our definition. So see, when we're dealing with imaginary numbers or complex, whatever you want to call it, we actually can't take the square root of a negative number, but we found a way around it. Okay, so we just hide the negative below another radical, and we just call it this variable I. Okay. If it's a square root of a negative number, it's going to be I. Okay. So if I were to give you something like, I don't know, square root of a negative 144, what would that be? 12I. So really 12 times the square root of negative 1, because I can't do anything with that negative. Okay. The complex numbers are actually super, super important to us. In fact, if we didn't have a knowledge of complex numbers, something very near and dear to your hearts would not work. Your cell phones. Okay, we use those with part of our frequency on the towers. Okay, now I'm not going to worry about getting into it right now, but it does have applications. Because people always ask, when are we going to use this in the real world? Technically, you kind of use it every day. But let's go ahead and finish this up. So, is it complex? Yes. Real or imaginary? This one's definitely imaginary because I have an I. Now, because it's imaginary, you'll notice there are no groups below it. I can't go any further. So that's all I can classify it as. Okay. How we doing? What do you guys think? Okay. All right, well, let me go ahead and pass out your assignments. Okay, this is covering exactly what we just did here. And when's the assignment going to be due? Okay, tomorrow. Okay, it's going to be due tomorrow. Good. And there's just a couple things I want to point out on this before I turn you loose and let you start looking at it. Okay. All right, so first, at the very top, where it's giving you a definition for C and D, let's go ahead and throw in there that they're positive numbers, okay? Because what's going to happen, odd numbers less than 9, that could include what? Negative, so that would be an infinitely large set, and we're not going to deal with that. Okay, so let's go ahead and say for both C and D, we're going to say they're positive odd and positive even. So it's going to give you nice sets to work with. Now, let me ask you a question. 0 can be considered even because it is divisible by 2. 0 divided by 2 is still 0, right? But will 0 belong to set D? What do you think? No, because I said what? There you go, because I said positive, and 0 is neither positive nor negative. Okay, so that kind of helps you out with C and D. You'll notice on this why I'm an amazing math teacher. You'll notice how the first one goes to 12. What's the very next problem? 11, 12, because I teach math. So I just made a typo. I was doing the sections differently, so don't worry about that. I'll just refer to it as like first 11, first 12. Yeah, second 11, second 12. Don't let that bother you. Okay. Everything else should be hopefully very straightforward. Now, the other classes, they decided they wanted to work number 11 together. Do you guys want to work one together, or do you feel confident? Okay, let's go ahead and take a look. It says, of 50 cat and dog owners surveyed, 25 have a cat. 10 owners have a dog and a cat. How many owners have a dog? draw a Venn diagram in order to help. Okay, so let's visualize what's happening here. So I'm going to draw my universe, put that little U on the outside. Now, if I were to label it, how many, I don't want to call them items, like people are in the survey? 50. Okay, so the universe has 50 people total. That's all we're looking at, right? We're only interested if they own dogs and or cats. All right, so are there people who own both? So what am I going to notice with my circles? Yeah, they're going to be connecting. They're overlap. Okay, so let me draw it like this. Okay, so let's say dogs are on the left, cats are on the right. Okay, so do we know anything immediately?
Yes.
What do we know, Andrea?
Yes, but cats.
Okay, and
10 have both.
there we go. That's what I want to focus on. We know 10 people own both. So I'm going to put the 10 right there in the middle. Okay. Now, Andrea said that we have 25 people who own cats. Does that mean I need to put 25 right here? Why is that wrong? There you go. Think about it like this. Even if you own a dog and a cat, can you still be called a cat owner? Yes. Okay. So we've already accounted for 10 of those 25 people because the entire circle C, the cats, has to be 25. So what should go there? 15. So I know that while 10 people own a dog and a cat, 15 people only own a what? A cat. Now, here's the thing. Whatever number we decide to put here, that value plus 10 plus 15 should total what? Should total 50. So right now, it looks like we're at 25. So how many people just own dogs? Okay, 25. Is everybody okay? Does everybody see how I reasoned my way through that? Now, what's the question? Does it say, it says how many owners have a dog? Oh, there we go. So if we're looking at this, I want to know the number of people who own a dog. Now, it's very specific about how it's written. If it had said how many people own just a dog, then we would say 25. But because it says how many people own a dog, it doesn't say anything about whether or not they can own a cat. So what would you say? I'd say 35. There you go. Does that make sense? Okay. Is there anything else on there that's kind of causing issues for people? Brandon?
Do we have to put 50 inside the
You don't have to. I mean, I'm not going to be a stickler about that. Like, if I'm going to ask you to draw a Venn diagram, I'm going to be looking more for inside the rectangle. But I mean, if you want to go ahead and put, like 50 right there, that's great. Okay. All right. Okay. So hopefully that problem wasn't too rough. It's a dog, see? I do want to thank you guys for helping me out on that one. Helping me out. Come on. You'll laugh later? Okay. Now we got that awkward silence after my joke fell flat. So. Huh? Why's it got to be like that? Who, me? Or what? Oh.
Never mind.
I was like, what? Okay. This recording got really strange all of a sudden. Is there anything else on the homework we want to take a look at? Anything else you're looking at and you're like, I'm not really sure what to do? No? Okay. Then I'll go ahead, turn you guys loose. The bell rings at 36, so we only have a few minutes left, so I apologize. I'm going to try to give you as much time as possible, to work on your assignments in class. Okay. But if you need anything, please let me know. I'm here in the morning, 7:45. If you want to come in, I've already had people coming in every day. So, otherwise I'm just sitting here twiddling my thumbs. Hey. So it's complex. It's real. Can we say it's rational?
Yes.
Yes.
And then it's not.
And then we can't go any further. That's right. Good.